Okay, so we're going to finish this lecture on curve lengths. But before I get to the short differential formula, let me just tell you that there's a practice problem here if you want to give it a try here. And so now again, this is like the last one from the last video. So to solve this one, you actually need to use that second formula where you use dx over dy in the formula rather than dy over dx, because that's what I did there, and the answer is given for you. Okay, so let's look at the short differential formulas. These formulas can frequently be written in terms of differentials instead of derivatives. And so the formulas can actually be expressed in this form. So we'll say that the length, I'm sorry, I left out, let's see. Okay, we'll say that the length of your curve can actually be expressed as the integral from a to b times the square root of dx squared plus dy squared. And then we actually call this this expression square root of dx squared plus dy squared, we call that ds. So since that length can be expressed using that formula, then we might as well just go ahead and say that that integral, we're just integrating from a to b ds. Okay, now, and then through proper manipulation of this formula, we can show it's the same as either one of these formulas. So in other words, either one of these formulas will work. Of course, the formula on the left assumes that you're integrating from x equal a to x equal b, and the formula on the right assumes you're integrating from y equals c to y equal d. Okay, so let me just go ahead and do one more problem for you. Let's determine the length of the function y equal the natural log of secant x on the interval as x goes from 0 to power 4. Okay, so let's go ahead and find the derivative of this function with respect to x. So if I take the derivative of y with respect to x, that would just be 1 over secant x, and then times the derivative of secant, which is secant tangent x. So I'd have 1 over secant times secant tangent. Well, then secant x over secant x actually cancels, and so you just get tangent x. Okay, well now, if I plug that into this first formula here, then what I'm going to get is the square root of 1 plus tangent squared x, and then I'm going to integrate from 0 to power 4 because I'm actually integrating with respect to x. Now if I was integrating with respect to y, I'd really have to find what the corresponding y values would be for x equals 0 and x equal power 4. But I'm integrating with respect to x, so I would go ahead and use those limits 0 to power 4. Now 1 plus tangent squared is actually, this is actually secant squared. So because tangent squared x plus 1 is secant squared, and then if you take the square root of secant squared, you just get secant. And then in an earlier video I showed that when you integrate secant x, the formula to integrate secant x is it's the natural log of the absolute value of secant x plus tangent x. And so now we want to integrate that or evaluate that from 0 to power 4. So let's put power 4 in. So I get the natural log of secant power 4 plus tangent power 4 minus the natural log of secant 0 plus natural log of the absolute value of secant 0 plus tangent 0. Okay, so let's do this one term at a time. secant pi over 4 is square root of 2, tangent pi over 4 is 1. So here you'd have the natural log of square root of 2 plus 1. So that's that. Now you'll notice there's nothing else. So let me show you why there's nothing else. When you evaluate this at 0, you know that secant of 0 is 1 and tangent of 0 is 0. So 1 plus 0 is 1. But this would actually be the natural log of 1. And the natural log of 1 is 0. So therefore there's nothing to subtract from this term. So you actually just get this, the natural log of the square root of 2 plus 1. And I know I can eliminate the absolute value because I know the square root of 2 plus 1 is a positive number. Okay, so that pretty much ends this section on finding curve lengths. And there's another practice problem that you can do here. And on this one, I actually suggest you do this one with the second formula up here. So you would integrate this from y equal 1 to y equal 4, but then you would actually find the derivative of x with respect to y and square it and plug it into the formula. And there's your answer there. So the answer I got was 14/3, and the integral I got was, I ended up with the integral from 1 to 4 square root of y dy, and then when I integrated that I got 14/3 for the length of my curve. Okay, so the next video we're going to use integrals to calculate moments and centers of mass. So that's what you'll see in the next video. That'll be the next application of integrals.